Hello, my name is Kevin Craig. I have created 12 modules on electronics and measurement for mechatronics. Modern engineering practice requires that engineers model, analyze, and predict before they measure. What is mechatronics? The diagram you see I created in 1995 as a professor at Rensselaer Polytechnic Institute. It now is used worldwide to represent the field we know as mechatronics. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process, from the very start of the design process. These modules present the fundamentals of electronics and measurement for mechatronics. This module is on pulse width modulation, PWM. Here is a pulse width modulated signal, a PWM signal. The period of the signal is constant. It doesn't change. The signal is either low or high. The portion of the period that the signal is high is called the duty cycle, expressed as a percentage. So the duty cycle is delta T divided by the period. Here the duty cycle is low, which will lead to a low average voltage. Here the duty cycle is high, which will lead to a high average voltage. An introduction to pulse width modulation. What is it, and why is it so widely used? All engineers need to know. As engineers, there are many components and devices we use every day that we treat as black boxes. We only are concerned about the inputs and outputs of the black box, and this is acceptable provided we know the operating range and limitations of the device. The same can be said about certain concepts and techniques. We routinely use them and they work, but maybe we really do not understand why they work. As fundamental performance limitations and safety come into question, a deeper understanding becomes necessary. In addition, innovation demands understanding. The widely used pulse width modulation, PWM technique, may fall into this category. Most engineers use it every day to drive a variety of devices, but only a few know why it is used and how it works. A pulse signal is defined by its amplitude and pulse width. A periodic pulse train has a frequency, pulse repetition rate, and a duty cycle, the ratio of pulse width to repetition period, varying between 0% and 100%. In pulse width modulation, we modulate the duty cycle while keeping the period fixed. A PWM signal can be generated by microcontrollers which operate in the digital domain. While an analog signal is continuous in both time and amplitude, a digital signal is discrete in time, that is, sampled at a certain rate, and quantized in amplitude, using a finite number of bits. The output of a microcontroller is typically either digital or pulse width modulated. The PWM signal typically varies between 5 volts and 0 volts, high and low, and thus can be used to turn an electric power switch, a transistor, on and off, and control the amount of power delivered to a load. Why would anybody be interested in this type of signal? Pulse width modulation avoids losses normally incurred when a power source is limited by resistive means. In pulse width modulation, the average power delivered is proportional to the modulation duty cycle. Thus, the switch circuits used to control the voltage across or current through a load have low power loss as the switching devices are either off, no current, no power loss, or on, low power loss due to low voltage drop. The PWM signal with sufficiently high modulation frequency can be augmented with a low-pass filter to smooth the pulse train and recover an average analog waveform. Pulse width modulation has been called a poor man's digital to analog converter. Here we see a pulse width modulated signal. The sine wave is the waveform we wish to convert to a PWM signal. The triangle wave is the carrier wave at the frequency of the PWM signal. That frequency is constant. Its period is constant. To convert the sine wave to a PWM signal, in any period, I examine the triangle wave and the sine wave. The portions in any period where the sine wave is greater than the triangle wave, the PWM signal will be high. In any period where the triangle wave is greater in amplitude than the sine wave, PWM signal will be low. We'll examine this a little more closely in a few slides. Pulse width modulation is a technique in which a series of digital pulses is used to control an analog circuit. The length and frequency of these pulses determines the total power delivered to the circuit. PWM signals are most used to control DC motors, but have many other applications ranging from controlling valves or pumps to adjusting the brightness of an LED. The digital pulse train that makes up a PWM signal has a fixed frequency and varies the pulse width to alter the average power of the signal. The ratio of the pulse width to the period is referred to as the duty cycle of the signal. For example, if a PWM signal has a 10 millisecond period and its pulses are 2 milliseconds long, that signal is said to have a 20% duty cycle. PWM can be used to reduce the total amount of power delivered to a load without losses normally incurred when a power source is limited by resistive means. This is because the average power delivered is proportional to the modulation duty cycle. With a sufficiently high modulation rate, passive electronic filters can be used to smooth the pulse train and recover an average analog waveform. High-frequency PWM power control systems are easily realizable with semiconductor switches. The discrete on-off states of the modulation are used to control the state of the switches, which correspondingly control the voltage across or current through the load. The major advantage of this system is the switches are either off and not conducting any current, or on and have, ideally, no voltage drop across them. The product of the current and the voltage at any given time defines the power dissipated by the switch, and thus, ideally, no power is dissipated by the switch. Realistically, semiconductor switches are non-ideal switches, but high-efficiency controllers can still be built. How does one generate a PWM signal using op-amps? A PWM signal is generated by comparing a triangle wave signal with a DC signal. This 3 op-amp circuit produces a triangular wave and a variable pulse width output. U1A and U1B form a triangle wave generator. U1A is configured as an integrator and U1B as a comparator with hysteresis. At power up, the comparator's output voltage is assumed to be 0. Here is the output of that 3 op-amp circuit. Here we see the triangle waveform, which is the carrier waveform. And here we see the pulse width modulated signal, where the input voltage is 1.8 volts. And you see the duty cycle is this delta t, the portion of the fixed period that the signal is high, divided by the period. That's the duty cycle, and we express it as a percentage. Here we see a MATLAB Simulink diagram that demonstrates the pulse width modulated signal. The analog signal I wish to convert to a PWM signal is a 10 Hz sine wave. The reference signal I will use is a triangle wave of 500 Hz. Notice that this frequency, 500 Hz, is 50 times the frequency of the sine wave I wish to convert to a PWM signal. The reference signal frequency should be much, much greater than the frequency of the analog signal I am converting. When I compare these two using a relational operator, if the analog sine wave is greater in amplitude than the triangle wave, the relational operator will output a 1. If the amplitude of the sine wave is less than the amplitude of the triangle wave, the relational operator will output a 0. This is a Boolean output. I use this gain block to convert the Boolean to a double precision number. I then adjust the magnitude of the double precision number so that when it is 1, I will then multiply by 5 and make it 5 volts. When it's 0, it will stay 0. I use 2 scopes to see the results of this demonstration. The first scope will compare the analog sine wave to the PWM signal. The second scope will compare the analog sine wave to the triangle reference signal. The frequency of the triangle reference signal can be set, and we'll discuss its relationship to the frequency of the analog signal we are converting in a few slides. Here I see the 2 scope outputs from the demonstration. The first scope shows the analog sine wave, 10 Hz, 0 to 5 volts, which I wish to convert to a PWM signal. Also seen is the 500 Hz triangle wave. In the other scope, I see the 10 Hz, 0 to 5 volt analog sine wave and the resulting PWM signal that represents the analog sine wave. Let's zoom in, look more closely to understand what's happening in these 2 scopes. Let's zoom in on the 2 scope outputs to better understand what's happening. In the top scope, I have a triangle wave in purple, which is 500 Hz, and it's 0 to 5 volts. The yellow curve is my analog sine wave, 10 Hz. In the bottom scope, the yellow is my analog sine wave, 10 Hz. And the purple is now the PWM representation of that analog sine wave. How was this PWM representation generated? Well, I have solid yellow lines separating each period. So if I look at this period between these two yellow lines, and I look at the points where the sine wave intersects the triangle wave, and I've shown this with dashed lines, I note that in the portions of the period that the sine wave is greater in amplitude than the triangle wave, then the PWM signal is high. So it's high in this portion of the period, and it's high in this portion of the period. And I see that down here. The signal is high here, and it's high here. In this middle portion, where the triangle wave is greater in amplitude than the analog sine wave, the PWM signal is low or zero. So it's either high, 1, or low, 0. And the high has been multiplied by 5. So when it's 1, we get 5 volts. We can use pulse width modulation to generate analog output. Pulse width modulation can be used as an inexpensive digital to analog, that is D to A, converter. A wide variety of microcontroller applications exist that need analog output, but do not require high-resolution digital to analog converters. Conversion of PWM waveforms to analog signals involves the use of analog low-pass filters. In a typical PWM signal, the frequency is constant, but the pulse width, the duty cycle, is a variable. The pulse width is directly proportional to the amplitude of the original unmodulated signal. Here we see 3 graphs. The top graph shows the typical pulse width modulated waveform with a constant period and a varying duty cycle, W1, W2, W3. A frequency spectrum analysis of this PWM signal will show a fundamental component and higher harmonics. The output of the low-pass filter will have a desired bandwidth, and that bandwidth should be much, much smaller than the fundamental frequency of the PWM signal. And the relationship here shows the frequency of the PWM signal equals K, some constant, times the bandwidth of the desired output from the low-pass filter. And K is much, much larger than 1. K will vary. If I choose the output of my RC filter to have a bandwidth of 4 kilohertz, then the PWM signal should have a frequency of, in this case here, I choose K to be 5, 20 kilohertz. If I take this 20 kilohertz PWM signal and I put it through my RC filter with a bandwidth of 4 kilohertz, what that means is that the minus 3 dB point will be at 4 kilohertz. The bandwidth is equal to 1 over tau in radians per second, which has to be divided by 2 pi radians per cycle to get hertz. And I know that tau for an RC filter is R times C. So I can choose R to be 4 kiloohms and C to be 0.01 microfarads. And that will give me a minus 3 dB point or bandwidth of 4 kilohertz. If I then look at the amplitude ratio in dB at 20 kilohertz, which is 20 times the log to the base 10, which converts amplitude to dB, times the amplitude of my output of the RC filter at a frequency of 20 kilohertz, I get minus 14.2 dB. If this minus 14 dB attenuation will not suffice, then a higher order active low-pass filter may be necessary, or use a higher PWM frequency. Here I have a MATLAB Simulink pulse width modulation low-pass filter demonstration. I'm converting a sine wave, my analog signal that is 10 hertz, which I set for this example, that I want to convert to a PWM signal, and then take that PWM signal and try to convert it back to the original sine wave. To convert the sine wave to a PWM signal, I use a reference triangle wave, which I will choose to have a frequency of 200 hertz, or 20 times the frequency of my sine wave. Using the steps previously described, where I compare the analog signal to the reference triangle signal using the relational operator, converting the Boolean output of that relational operator to a double precision number, then amplifying the high value from 1 to 5, set amplitude to 5 volts. I then get my PWM signal, which I then, in this scope, compare to the analog sine wave. If I then take this PWM signal and I put it through a RC low-pass filter, and this represents the transfer function for the RC low-pass filter, where now I've used K to represent something different. Poor choice by me, but here K will set the cutoff frequency of the filter, which should be about 5 times less than the PWM frequency. So here in this expression, K is 0.2. It sets the bandwidth of this RC filter so that the bandwidth is 5 times less than the PWM frequency. And then the scope will show the analog sine wave that we started with now the filtered PWM signal from the RC low-pass filter. Here we see the result of this demonstration. In yellow, we see the analog sine wave 10 hertz, 0 to 5 volts. In the demonstration, we converted that to a PWM signal, which we've shown in previous slides what that looks like. I then took that PWM signal and put it through an RC low-pass filter with a bandwidth 5 times less than the frequency of the reference signal for the PWM conversion. The result of that transformation of the PWM signal to a filtered analog signal is shown in purple. And of course, by varying the parameters, the choices for the ratios of PWM frequency and the bandwidth of the RC filter will produce different results. This concludes the presentation of pulse width modulation. Thank you for your attention.